In our third example, we're looking for a current I of t for time greater than 0 for this circuit shown below. And so we're assuming switching happens instantaneously. The switch has been in position A for a long time, and then at t equals 0, it's going to move to be in position B. And so this example is going to be a little different for a couple reasons. One, we can see that our initial inductor current can be given by circuit configuration itself as opposed to just given in a problem statement. And so the same is true for capacitor voltage as well. The second thing that's going to be different about this example is that we see we don't have values for our sources or our components. So we're going to be dealing with variables. And so ultimately what we want to do is show that you can come up with some general equation for a circuit, but we also want to compare the equation we get for this specific circuit to previous analysis that you've seen for RL circuits in the time domain. So let's start this example the same as we have the previous two examples by transforming our circuit to the S domain. So transform our circuit to our S domain. Okay, so as we've seen in the last two examples, we have no change for our resistor. So no change for R, it's just going to stay a value of R. This voltage source in the middle, we notice that the switch is closing at T, or it's moving to position B at T equals 0. So before T equals 0, our voltage has no input, and then it's jumping up to a value of V0. So again, we can plot what this looks like over time. So if we have our voltage, it's going to be coming up to a value of V0. And so for T less than 0, it's going to be 0. Then it's going to jump up to V0 and stay there. And so of course we can see that this is just going to be our step function times V0. So a scaled version of our step function. So we have our voltage source is then V times U of t, and taking the Laplace transform of that is V0 over S. Our L value, so we have our inductance, is going to have an impedance of S times L, but assuming that our switch has been in position A for a long time, we're going to have some initial current due to this current source here. So if our switch has been in position A for a long time, DC steady state, our inductor behaves like a short circuit. All of this current I0 is going in this loop here. So we're going to have an initial current of I0. So what that means then for our S domain representation of our inductor is that this impedance SL is either going to have a voltage source in series or a current source in parallel. So we're either going to have a voltage source, and so the value of this voltage source is going to be L times I0, and it's going to be in series with that inductor impedance, or we're going to have a current source, and so the value of our current source is going to be I0 over S, and that's going to be in parallel with the impedance from our inductor. So just like we saw with our previous example, we want to be careful about voltage polarity or current direction, depending on which circuit representation we choose. So be careful with voltage polarity / current direction. And so again, just refer to what you have in your notes. For an exam situation, of course, your note sheet, make sure you have that on there. Because the current direction and voltage polarity, you want to make sure you have that right, otherwise you'll get an incorrect answer. So for this particular case, we can see our circuit for t greater than 0, which is what we're interested in, is just going to contain our voltage source, our resistor, and our inductor. If we're looking for this current, our mesh current is going to be attractive because once we find our mesh current, that's the value we're looking for. So in order to keep this as one mesh, the better option in my opinion is to use this voltage source in series option. Again, that's not to say you have to do this. By all means, you could do the other method of the impedance in parallel with the current source and use, for instance, node voltage method. Again, if you have questions about how to do that or you want to see that done another way, just let me know and I'm happy to go through that. But if we, for this example, let's say we're going to go with this L-I0 voltage source in series. So we have our voltage source that's being switched in, so we said that's going to be our V0 over S value. And we have our resistor, which is unchanged. And then our inductor is going to be replaced by the inductance, which is going to have impedance SL, and a voltage source in series. So negative polarity at the top, positive at the bottom, and we get something that looks like this. So this is R, SL, Li0, and our inductor current here in the S domain is I of S. One thing to note, we're not going to investigate it in this problem, but if, for instance, we were interested in our inductor voltage in this initial problem, so say we had VL of T, that would correspond to the voltage across both the inductor impedance and the voltage source. So this would be our VL of S. So again, just something to keep in mind, but we're not going to look into it in this particular problem. So as advertised, if we want to analyze this with our mesh current, we can see it's just one mesh. So we're just going to have one mesh equation. So if we write our equation around the mesh, or more simplistically, we can just say KVL around this loop. So KVL around our loop, we can start any point, go in either direction, but let's say we start here and we're going to go in a clockwise direction. What we have then is negative V0 over S plus R times I of S plus SL times I of S minus Li0. We're back where we started, so we set that equal to 0. And so what we want to do is we want to solve for our IS because ultimately what we want to do is find IS, inverse Laplace transform to get the I of t that we want. So solving for that IS, we can say IS is equal to, so sort of combining a couple steps, we can think about moving these terms without IS over to the other side. So if we do that, we're going to have a V0 over S plus Li0, and then we're going to divide by the terms here after we factor out our IS. So that's going to be SL plus R. So we have divided by SL plus R. And so what I'm going to do is go ahead and split this into two terms. So I'm going to say this is V0 divided by S times SL plus R plus L times I0 divided by SL plus R. And so the reason I'm doing that is because really we know that this I0 term here is just going to be some value. So in the next step we can say this is already sort of done. We don't have to consider that in our partial fraction expansion. So I'm kind of getting ahead of myself, so let me write this next line. So we have our IS. So sort of just playing some games here. Bear with me, we'll see why I want to do this later on. But let's divide through by L. So I have then V0 divided by L in the numerator of that first term. And I'm going to have S times S, so I've divided by L in the denominator as well, plus R divided by L. And then we're also going to divide by multiply by 1 over L times 1 over L here. So we have I0, so we've divided the L out. And then here we have S plus R over L. Okay, so again, we can keep in mind that this is a constant. So if we were to actually have this circuit, this would just be some value, for instance, maybe 1 amp, 0.5 amps, 3 amps. It's going to be some number. So we already know what this number is, so we could inverse Laplace transform this pretty easily. So we don't need to sort of break that apart using partial fraction expansion. That's not necessarily true for our V0 over L term. So what we can do is we can write this then as K1 over S plus K2 divided by S plus R over L, because we had the two poles in this expression here, so we need to split that up. And then we still have our plus I naught divided by S plus R over L as our other term, where we only have the one pole in the denominator, and this is a constant value. Okay, so at this point we can use our method of residues. We have distinct real poles in the brackets there for our K1 and K2, so we can say, let's go ahead and find those. So our K1 is going to be our V naught over L divided by S plus R over L evaluated at S equals 0. So if we do that, we get V naught over L divided by R over L. We can see our L's are going to cancel out, and we get V naught over R. Similar thing for our K2. We have now V naught over L divided by S evaluated at S equals negative R over L. So plugging in that, we have V naught over L in our numerator divided by negative R over L. Our L's again are going to cancel out, and we're left with negative V naught over R. Okay, so now knowing these values, we can come back to this expression here, and we can take the inverse Laplace transform using our known tables. Well, actually, let me first write this out explicitly just so we can easily see it. So we have our IS is going to be equal to, so let me move that down a little bit. So we have our IS is equal to V naught over R divided by S plus a negative V naught over R divided by S plus R over L plus our I naught divided by S plus R over L. So now we can inverse transform this pretty easily. Again, it might be a little awkward at first because we don't have numbers here. But of course we can think if we knew values for R, L, and V naught, these would just become numbers. So again, sort of a little different way of doing this example. So we can get a general expression then for our I of t in this circuit as V naught over R minus V naught over R. So using our frequency shift property, we then have e to the minus t over tau. And so I'll define that tau here briefly, plus I naught e to the minus t over tau. And let's define this for t greater than or equal to 0. And so this tau is equal to L over R. And so what we can notice is that by defining this as t greater than 0, I don't need to explicitly write u of t. So no need for our u of t with this present. So as long as we have that t greater than 0, that's essentially saying the same thing as multiply that whole thing by u of t. And so this should look pretty familiar from when you've analyzed RL circuits in previous classes. And so we can actually take this a step further, and let's look at this equation a couple different ways by grouping the terms a little differently. So let's first of all say we can write this as I of t is equal to, and so let's group the two terms that are being multiplied by a decaying exponential. So we have I naught minus V naught over R, and both of those are multiplied by e to the minus t over tau. And then our other term is just the plus V naught over R. So what this represents is we have this first term, which is going to be our transient response, or our response that is changing over time. And then the second term is just going to be our steady state response. Okay, so that's one way we can look at it. Let's look at a slightly different configuration where we sort of group just this term by itself because it's related to our initial conditions, and then group these two terms that are related to that voltage source. So doing that, we can say that our I of t is equal to, from our initial conditions, we have I naught e to the minus t over tau plus v naught over r times the quantity of 1 minus e to the minus t over tau. And so looking at this configuration, we can see that this first term is something called our natural response. And so basically that is what would happen if we took away that current source and we never switched in the voltage source. We just let the system decay over time, the voltage decay over time. And then the second term is our forced or step response. And so what this is a response to that voltage source being switched in. And so again, this sort of highlights the advantage of this Laplace analysis, that we're able to get our natural and our forced, or we can think about it as our transient and our steady state response all in one go. So we're not having to do separate analysis to get one or the other, we get it all at once. And so again, we should recognize this equation as the same equation that we saw in ENG 201 when analyzing first order circuits in the time domain. So it's always good to see that our analysis is giving us the same thing that we have found using a different method.